Syzygy, episode 85, Lucy in the Sky with Trojans. And welcome back for another edition of the Syzygy podcast. My name's Chris Stewart. Across the table in her office from the great Dr. Emily Brunsden. Emily, how you doing?
Hello. I'm very well, thank you.
Good. Well, I say you're the great because it's great to see you again, and in person for the second time in a row. Third time in a row. Gosh, time is just flying, isn't it? This is nuts. Listen, today we're going to be talking about something that we talked about last week, but in a slightly different way. Last week we talked about Jupiter and its great red spot, giant red, what did we call it again?
Great red spot.
Great red spot. I got it right the first time. And we'd never talked about Jupiter really in any detail before. Well, we're going back to Jupiter again this time. And we're not the only ones going to Jupiter. Emily, what or who is going to Jupiter this week that we're excited about?
Well, our friend Lucy's just off for a little sojourn.
Lucy is in the sky right now with diamonds, presumably?
Well, we'll get to that.
Right, okay. So what or who is Lucy?
So Lucy is a space probe that has been launched on October the 16th. So for us recording now, that was just last week.
Just a little while ago, yeah.
Which was very exciting.
And that all went well, all fine.
Yeah.
Lucy's good,
Went
fine, up there, kicking, doing the thing.
Yeah, well, on the way.
Yeah, okay.
On the way. And Lucy is off to look at some of the Trojan asteroids, which are in the vicinity of Jupiter.
Okay, Trojan. So why Trojan asteroids? What makes them Trojan asteroids?
So, well, there's two different ways you could answer that question, I guess.
Right,
One of them is the naming convention.
Okay,
So
yeah.
Trojan comes from the Trojan War. So because, we've got some Greek and Roman descriptions of the planets. You've got Jupiter as the big god, if you like.
Right, okay, that kind of makes sense. Is it because the asteroids are all in the shape of a big horse and there's soldiers hiding inside and they're giving themselves to Jupiter as a gift? No, it's not.
That would be nice.
That's kind of cool, but
Yeah.
it's not
No,
that. It's
no.
not Trojan horse asteroids. No.
They're just called the Trojans, and they're individually named after people famous from the Trojan War. So if you have read your Iliad, particularly,
It's been a while.
then you might remember some aspects of the Trojan War. But basically, there were the Greeks and the Trojans, and they fought over the city of Troy for a while.
It happens, yeah.
Yeah, and so that was quite relevant to Greek and Roman mythology. And so when, talk about Jupiter and you name things, one of the traditional things we name, say, moons and things like that, is after things that are related to the parent planet.
Sure, you go on a theme, right?
Yeah.
And so these are Trojan asteroids. But where are they? I mean, this probe, Lucy, is not going to Jupiter per se. It's going in the vicinity of Jupiter. Where are these asteroids?
Yeah, well, we actually very handily talked about these Lagrange points. Was it the last episode, I think?
I think well, hang on. That's in reference to a particular other spacefaring thing. So it's two episodes ago when we were talking about the James Webb, or Just Wonderful, Space Telescope, which is going to be at the L2 point, the Lagrangian point L2, which is the sun and then the Earth, and then there's L2, sort of outside, which I guess strictly speaking is a syzygy, is it? Hey, we got the syzygy bell back again. Syzygy being a lineup of celestial bodies. Does this count?
Yes,
Does
it does,
JWST count as a celestial body?
Absolutely.
Totally. Okay. So L2 is one of 5 different special points in an orbit of the Earth around the sun, or indeed orbit of anything around the sun. And let me get this right. It's where you've got a special, it's a mathematical relationship, but it's kind of a special balance of the pull of gravity from the Earth and the pull of gravity from the sun means that at this point outside of the Earth's orbit, further out, it can still orbit at the same rate around the sun as the Earth. It keeps up with the Earth because of that extra pull from the Earth.
Absolutely,
right?
yep.
So that's L2. But there are other L's as well. There's an L which is sort of forward of the Earth in our orbit, and there's one which is behind the Earth in our orbit, and there's another one which is towards the sun, and there's another one on the other side of the sun. All of these different L Lagrangian points. But you could do that with any orbiting thing, right? And so Jupiter has its own.
It absolutely does. And Jupiter's got quite a lot of gravity. Let's not forget.
Yeah. So those would be pretty amazing Lagrangian points. So, maybe not surprising that there might be something hanging out there.
Absolutely. Yeah. So when we talk about the Trojan asteroids, they're hanging out at L4 and L5, which are the 2 points on Jupiter's orbit. One is ahead of Jupiter by about 60 degrees in its orbit, and one is behind Jupiter by about 60 degrees in its orbit.
That's quite a lot. So these aren't really close, because Jupiter's orbit's really big, right? That's a really big circle ellipse in space, yeah? And so 60 degrees around from where Jupiter is in its orbit, there's a lot of gap there. So it's kind of really impressive to me that Jupiter, or indeed anything, can have that kind of influence out at, like, you wouldn't expect anything to be there. But apparently there's a lot of stuff there.
Absolutely, yeah. So we've got two what we call camps of asteroids.
Nice.
Yeah, so we've got the leading camp, which is the Greek camp of these Trojan asteroids. And we've got the trailing camp, which is the
Trojan?
Yeah, the Trojan camp.
There you are.
Yeah.
I'd like the way that they've really gone deep on it. Like, if we're going to go with a naming convention based on mythology, then let's really go in hard. Yeah? Let's keep naming them, we'll call them camps, and we'll give them little names and all the rest of it. So how many? How many asteroids in each camp?
Oh, do you want to take a stab at this? Because this was going to be part of my stat attack for today.
Oh, well, should we save this up for a proper stat attack?
Well, let's do that then.
Okay. All right. Okay. I got a question, though, before we move on from this, right? If you're telling me that Jupiter has Lagrange points, right, and L4 and L5, you said? These are 60 degrees, and there's a bunch of stuff there, yeah? Is that true of Earth as well? Is there stuff hanging out just out there in space around Earth's orbit at Earth's L4 and L5?
That's a fabulous question, and actually we think we have discovered one Earth Trojan.
Really?
Yeah.
That's
So we still
so
call
cool.
them Trojans, even though they're for other planets, just
Right.
because Jupiter's kind of was the first and you found them all there. But yeah, other planets do. And I guess most famously, Neptune has quite a lot of Trojans.
Right, okay.
I think
Saturn, I guess, would as well, maybe? Because it's big.
Yeah. Well, I haven't seen so many from Saturn. I know Neptune has 28. Mars has 4.
Right. Earth, we know, has at least one.
Yep.
Yeah.
And our little Earth one is really, really cute. It was only discovered in 2017. And so it's kind of
Wow, that's really recent.
Yeah, but the thing is that they're quite small. You know, the Earth doesn't have a lot of gravitational influence, so it's not a big heavy hitter when it comes to gravity in the solar system. So the things that it can capture and kind of keep in these points naturally, apart from the stuff that we shove up there, tends to be fairly small. So it's just a kind of little thing.
Right. So we know much more about Jupiter's, presumably because there's a lot more of them. It's a bigger camp?
It's a much bigger camp.
Right.
They're bigger objects in general, and so they become a bit brighter, so they become a little bit easier to study.
What a weird idea, though, that there could be things which are, I guess they're not moons, right? They're not going around the Earth. It's not like another moon for the Earth, but they're going around in the same orbit, and they are gravitationally linked to the Earth. Like, that's a special place in our universe. And we don't know. There might be more. There might be a bunch of them out there that we just don't know. It's kind of weird.
Yeah.
Oh, yeah.
Remember when we talked about Hayabusa 2, the Japanese
Yes,
mission that
I
went
do.
and did some sampling of an asteroid and came back again? Well, actually, the orbit or the trajectory of that spacecraft was designed to go through the one of the, I can't remember if it's the leading or the tailing one of Earth's own Trojan sort of zones.
Oh, right. To go and have a look, see if there's anything there.
Yeah, didn't actually see anything, interestingly.
That's a shame.
Maybe there's not that many for Earth anyway.
There might be a few out there. That'd be kind of cool. But we're not talking about that today. We're talking about Jupiter and its Trojan camps. So presumably there's quite a few. We can get onto that in the stat attack. Lucy's going there, though. Is this the first time we've actually gone there as opposed to just viewing them from afar?
The short answer is yes. We
Right.
haven't gone to the Trojans before.
That's cool. So that's Lucy's purpose. That's what it's built for, and that's where it's on its way to. Stat attack wise, are we going to be talking about how long it's going to take to get there and all of that kind of thing?
course we
Okay.
are,
All right. Well, should we do a stat attack now then?
Let's do it.
Is
yeah.
it stat
Come
attack
on,
time?
Let's do it.
All right, Emily, hit me with stat attack then.
All right. Well, you started us off with the Trojans, so let's start.
I did,
in that
okay.
point.
Yeah, how many
there.
are there?
How many are there? Would you want to take a stab?
Look, pure guesswork, 1,000 in each camp.
Well, you do have to kind of put some limits on this because I'm being a bit mean. I haven't told you any parameters here.
No, I mean, I'm working on literally nothing. So you told me there's one that we know near Earth, and Mars has 4, and Neptune was like hundreds or something?
28.
Or 28. So 1,000? But okay, give me your parameters. Give me knowledge.
Okay,
Sure.
well, there's two different ways to answer this question. There's the ones that we know about, and there's what we expect to find there.
Right. Okay. Ones we've actually eyeballed.
Yeah.
And then there's sort of theory.
Yeah.
Sure.
So the first category, the ones we kind of know are there, there's probably around 7,000.
7,000 that we know of. Is that in total between the two camps?
Yeah, that's right.
Holy cow. Okay. So that's that we've eyeballed, in a sense. So how many could there be? Look, I'm going to go with an order of magnitude higher. I'm going to say in the high tens of thousands.
So of all the bodies that are above a kilometre, so we're not counting like little particles of this, that and everything else. So
We're not
everything
talking dust here.
bigger than a kilometre in diameter, we reckon there may be up to 1 million.
Good Lord. That's nuts. That's crazy. That's a huge, huge cloud of... And we're not even talking about the tiny little bits. We're talking about the big chunks. Like a 500-metre wide rock doesn't count in this. And there are like potentially 1 million? Are you kidding me?
Yeah, which is amazing because that's about the number that we think might be in the asteroid belt.
Why isn't this talked about more? Like that's nuts. Okay.
Well, we don't know that for sure, which is a big part of what Lucy's going to help us understand.
Yeah, we only know about the thousands that we've already seen. That's crazy. Wow. And over what kind of like area? How big are these areas?
Well, it's quite interesting. The biggest one's sort of about 200 kilometres in diameter, but that's kind of an outlier. That, there's very few that are around the 100 kilometre plus range, and there's even, fewer really that are above kind of 50 kilometres.
Right, so they're chunks. But what I was actually asking was how big is the area? Like how big is the camp?
Oh, quite big, yeah. So there's not like, don't imagine a tiny little point in space, because when we talk about L2 for space telescopes, it really is kind of like a little point in space that we orbit.
Well, yeah, I mean, JWST is kind of going out there and just doing a little circuit around this point in space, I presume, for sort of stability. You can't just sort of sit there. It's not going to work, but you can orbit around it. But that's presumably a very tight little orbit that's going to be doing there. So how big are these, like planet?
There's sort of tens of degrees of sort of, if you think if there's 60 degrees from Jupiter, there's kind of tens of degrees beyond that.
That's huge.
It's really huge.
Like I was about to say, is it kind of like Jupiter size? But that's massive.
Yeah, it's a really big area because it's not a point in a sense that there's a singular point where you can be in the same orbit as Jupiter. That's true. But you can also be on a slightly eccentric, slightly wobbly orbit.
Right.
And sort of be in that, gravitational, let's call it, stability.
Right. So would a lot of these chunks out there, a lot of the Trojans, the campers, would they be sort of orbiting around that point, or is it more complicated than that? Is it just sort of a big cloud?
They're orbiting around the sun still.
But I mean,
Jupiter,
but in their orbit around the sun, in their camp, would they be sort of orbiting around L4 and L5? Or
not so much. So they're still really like the center of their orbit is really the sun. It's just that they might have, instead of like a more circular orbit like Jupiter, they've got kind of they vary their distance from the sun a little bit more.
All right, next stat attack, hit me.
Right. So you wanted to know, next question, how long it's going to take to get there.
Yes. So
there's also two answers to this question.
Of course there is. Okay, well, so can we put some parameters on this then? Is Lucy going to visit only one of the camps?
No.
See, right. Okay, I'm catching up. So I'm going to guess that Lucy's going to go straight to one of the camps, but not via Jupiter, because if it gets a slingshot from Jupiter, that's going to make it go too fast. But I could be wrong. I'm going to guess it's going to take 6 months. I don't know. I have no idea how long it takes to get to Jupiter.
It's going to take about 6 years.
6 years. That's what I meant.
That's to get out to the first camp, that the Greek camp is going to be first, to the leading camp. So take about 6 years. As you say, you do need to use your gravitational slingshots to get out there. But what Lucy's going to do is use the Earth for that. So it's kind of going to wrap around the Earth.
6 years. I mean, yeah, thinking about it, 6 months is not nearly long enough. But 6 years. Wow. Is that how long it's taken for other missions to get out when we've gone to Jupiter? Is that how long it's taken?
Yeah, it depends. If you can speed it up if you do some sort of slingshots via Mars, for example. But you have to kind of get everything in the right place, which doesn't happen all that often.
Yeah. Wow. I sort of forget about the timescales involved. Being someone who's working on this mission must be really weird. Like, you'd put in all of this effort to get ready, and we got it on the launch pad, and it goes, and everything working, fantastic, it's pointing in the right direction, fantastic. Right, got to go and get another job for 6 years, you know, and then you come back and you do the thing in 6 years' time. Like, that's got to be really weird.
Well, there are some things that Lucy will do along the way. So there's at least one interesting thing that I'll come back to.
Okay.
So it's going to go to L4, the Greek camp first, and then it's going to kind of sort of come back in a big sort of wide loop. It's going to swing past the Earth again. So
come all the way back.
All the way back to Earth. Yeah.
Wow.
And then it's going to go back out to the second camp, the Trojan camp. So any guess when that will be?
Look, if it was 6 years to do the first one, at least that again?
Yeah, pretty much another 6 years. So 2033 is when we expect.
Wow, that's nuts.
The next visit.
Is the reason that it has to come back again via Earth because orbital dynamics are hard, right? You can't just, if you're out there. So which one's it going to first? The one in advance of Jupiter? Right?
Yep, that's right.
You can't just hop across. Like, you're going really fast around the sun. And you can't just sort of put the brakes on and let Jupiter just whip on past you and then speed up again and catch back up again. Then you've actually got to... We need to do a totally different orbital thing in order to get back out to where we're going. It's actually much harder than it looks like it is in Star Wars.
Absolutely, yeah. And remember, these Trojans don't really have a lot of mass, so it's not like you can use them to help you, really.
Yeah. So you're either going to take a huge amount of fuel and big rockets to sort of push you along in the direction you want to go and then stop you when you get there, or you use some really, really clever orbits that bring you to completely different parts of the solar system in order to just then nudge you out to where you need to be. Orbital dynamics is hard, really hard. Like, hats off to anyone who does that kind of calculation. When it swings via Earth, does that mean that it gets to, like, quick, just dump a whole lot of data down because it's much easier to do that because it's just there?
It's a good idea. I think it's built to basically transmit throughout the whole mission. So even part of the mission is to look at the broadcasts coming back from the spacecraft and sort of use that to probe the space in between Earth and the wherever it is at the time. Right.
Okay.
So
you're looking at not just the message itself, but how the message got to us. That gives you the message is the medium, as they say.
Exactly.
That's cool. Okay, cool. I would not have guessed that it needed to actually come back home in order to then go back out again, but there we are.
Right, so next question. How many Trojans is Lucy going to visit?
Well, I mean, I don't... if it's going to go all that way, right, I'm guessing that it's going all that way to do something that we couldn't just do from the comfort of our own lounge rooms, right? So we could... turn the best telescope that we've got and look at the biggest chunk and go, what is it? But if we're going to go to all the trouble and all the time and all the money to send something out there, then it's going to actually go there, right? It's actually going to go and have a really good, hard, close look. At the end of that statement, I have no idea what the answer to your question is. But as you said, there's not a lot of gravity, and landing on an asteroid's really hard. We've done that once.
Twice, I think.
Twice? I don't know. Pick a number. Half a dozen. I don't know.
Not bad. Not bad. 7, maybe 8.
Okay.
And we're flybying, not
landing.
Not landing.
Not landing, because landing's hard.
Well, then you got to get back upward and
that's
go
right.
back into an orbit, and that's all just really...
Yeah, and I mean, doing it once is hard enough. Doing that half a dozen or more times is really hard. But a quick flyby of, what did you say, 7 or 8?
Yeah. 7 definite. I think they might throw in an 8th if they sort of find one along the way.
Right, and presumably those are fairly... sort of broad brush adjustments to a trajectory that it's not like it can just come in and just loop around one of these things a bunch of times, because there's not a lot of gravity for it to use, and it won't be carrying a lot of fuel in order to do its thing. So you're trying to choose a trajectory which will take it close to the points of interest, and it'll just whang straight on past.
Yeah.
And take a lot of pictures on the way.
An incredible speed.
Yeah.
Go on.
Oh, I literally, You asked me these questions and I've got no frame of reference. For this one, I've got nothing. Literally nothing. So you may as well just tell me this one.
Yeah, so we're going to be flying by somewhere between 6 and 9 kilometers per second.
I mean, that's fast in anyone's language. That's really quite fast. Wow. Okay. So yes, it'll want to make sure that the camera is turned on and primed. Before
but there's some really cool Trojans that we're going to be visiting, right?
Yep.
And I thought I might as well write them down because they're, there's only 7 of them.
Do tell. What are we going to go and see?
Right. So, pens and pencils at the ready, especially if you're looking for names for your unborn children.
Yeah, good.
These are all good ones. So the first one is going to be Eurybates.
Eurybates or Eurybates?
Yeah, okay, my Latin is terrible.
Latin, Greek, whatever it is, yeah.
Yeah, Eurybates.
Classical scholars, write to Emily.
It's a 64-kilometre wide asteroid.
That's a sizable chunk.
It's got a moon.
It's got an asteroid with a moon.
An asteroid with a moon.
I didn't know that was allowed in the scheme of things.
Yeah, asteroids are allowed moons.
Yeah?
Absolutely. You're just not allowed moons.
Oh.
Well, we haven't found them yet. You're allowed them. You just
It's moons all the way down. Wow, okay.
Yeah. So the moon's called Quetta.
Sure.
We'll go with that.
We'll go with that.
Yeah. So that's quite cool,
So how big's the moon? I mean, if this thing's only 64... I mean, sorry, Emily, can I just interrupt you for a second here? This is a really long way away. This is 64 kilometres across, and we know it has a moon. How?
We can see it, basically.
Really?
Well, these things are very, very dim because they don't reflect much light. And, of course, they're very, very small. But we've been pointing big telescopes at these areas of the sky. And even some of our spacecraft like Juno have, as they've gone past, looked at the Trojan asteroids, for example.
But I mean, that's it's a it's a really long way away, and it's 64 kilometres across, and it's got a moon. How can you can't see that? That's like saying I could see an M&M in London from here. I mean, that's nuts.
Well, astronomers are good these days.
I tell you what, you're not getting paid enough, you people.
So once we're done with that system, then we're going on to...
Checks notes.
Yeah, hang on. I think
should have practiced this one first.
No, I couldn't read my handwriting there for a second, which is probably not going to make any difference to the pronunciation.
Give
at
it a
all.
go. What have you got?
Lucius.
How do you spell it?
Leucus. So it's kind of
Lucas.
Is the C hard or soft?
I have no idea.
No.
Again, classical scholars, please do tell, or indeed, astronomers who are actually studying these things as your job. Let us know. Write to us.
So this particular asteroid looks like a football or a rugby ball.
Yeah. Because we're well and truly into the territory of things which are not shaped by gravity here. Yeah. How big do you have to be before you're spheroided
it's a good question.
by the force of gravity?
Much bigger than this.
Because that's a planet thing, isn't it?
Yeah,
are you a planet? Are you not a planet? That's
think
one of the tick boxes.
Absolutely. Ceres is spherical. One of the big asteroids in the asteroid belt. But it's one of the biggest ones in the belt.
So roughly?
I don't remember.
Order of magnitude, doesn't matter. Okay.
Bigger.
So this is not that big.
Then we got Polymele.
Poly. We'll just call it Poly.
21 kilometres in diameter.
Mm-hmm.
Orus, who's 53.
Mm-hmm.
And that pretty much sums us up for the Greek camp.
Right, so we're just doing that quick flyby of how many were there? Was that 5? Was that 4?
1, 2, 3, 4.
4
But
in the Greek
camp. The moon
camp.
sort of counts as one as well.
With a bonus moon.
Yeah.
Call that a bonus.
I guess if you talk about objects, then yeah.
And
then we go
a speed of 9 kilometres a second as you whip on through. Hi!
And then we go across to the Trojan camp, and we've got a binary system, which is very exciting.
Okay, now hang on. What's the difference at the asteroidal level between a binary system and an asteroid with a moon?
Well, it's a good question. It basically depends on how big they are relative to one another.
Can I guess?
Go on.
Is it so when you've got two things going around each other, they will actually orbit around a common center? And is it that center of gravity is outside both objects? That it's a binary?
That's a good definition. Yeah, I think that's the best one. There are some sort of debates about what exactly it should be, because using that argument, then Pluto and Charon should be a binary planet.
Pluto's already got problems, though.
But,
that was identified some time ago. But I mean, to me, that would at least make sense, right?
Yeah.
If the center of mass is inside one of the objects, then that object is kind of orbiting around itself. And so that's the primary object and the other one's going around the outside, and that's the moon. That makes sense. But a binary is where they're orbiting around some dot in between them.
Yeah, some imaginary point in space.
Okay. See, I am learning stuff.
Yeah, so we got Patroclus and Menoetis.
Okay, nice.
Which are both about 100 kilometres across. So they're big.
They're big. Yeah.
So those are our sort of six-ish, 6 and a bit.
6 and a bit, 6 plus a moon.
Yeah.
Nice.
Maybe we'll add another one along the way.
Right, and that'll all be done somewhere around about, those last few, somewhere around about 2033. Wow, 12 years down the track. But we only have to wait 6 years for that first one.
Yes.
Cool.
Only.
Okay. What sorts of things are they going to be looking for when they get there? I mean, you said a minute ago there's parts of the mission which are en route, so we'll get to that in a second. But when they get there and just flinging themselves at enormous speeds past these chunks of rock, what are they looking for when they get there?
So there's 4 key parameters we want to measure for these asteroids. The colour, the composition, the spin, and the mass.
Okay. It's beginning to sound like particle physics here for a second.
It does, doesn't it? Yeah. And the quarks and the up and the downs and the
right.
right.
Okay, so sorry, colour, spin, mass, composition, as in what are they made of?
Yep.
All right, okay.
Well, they all kind of relate back to composition as well. They're not exclusive, right?
Sure. So,
and yeah,
I can see why composition is really interesting, because you want to know what these things are made out of, and presumably that would tell you or add a bit to the story of both where they came from and where the solar system came from and all
Absolutely. We're talking about origins. So at this point, I think it's a really nice we'll come back to what the origins that we're trying to figure out are, but we might as well segue a little bit into why Lucy.
Okay, I love a good segue. So yes, Lucy, the name of the spacecraft, which is, it's a nice name. Nothing against the name at all, but it is quite like it's a name. This is not sort of it's spacecraft X-16B. This is Lucy. So why Lucy?
So we're sort of looking at some of the fossils of how the solar system formed.
Right.
Are you getting a clue here with fossil? There's a very famous fossil / human remains.
Oh, good. There's a very small part of my brain going, you know this one. You know this one. I can't remember this one.
So Lucy is the name of one of the very first early hominoids that was discovered.
That's right. So that's why Lucy is named Lucy the spacecraft is named Lucy the spacecraft after Lucy the fossil, Lucy the hominid.
Yeah, exactly.
Really?
Yeah.
Huh. There you go. I thought you were going to say, well, we think there might be out there in the asteroid clouds, there might be little bits of really clumped together carbon, and maybe there'll be some little bits of diamond or something. It says Lucy in the sky with diamonds. I thought maybe that's where we were going.
Well, how was Lucy the fossil named?
Oh. Now you're really, this is segueing into segue after segue. I don't know.
It was named after the Beatles song.
Really?
Yeah.
Why?
Because all I know is they played the song very loudly in the camp the day that they found the fossil of Lucy.
There you go.
So
it does come back to the Beatles. I just missed the important bit in the middle there, which was the fossil. Right.
And it gets even more twisted. Because Lucy, the one that's in the sky, does in fact actually have on board diamonds.
Why? Why does Lucy have diamonds? That seems a bit superfluous to its mission.
It's just one of the instruments happens to use synthetic diamonds as part of its setup.
Okay, it's not just for bling.
No.
It's not just, I don't know, we've got a little bit of weight budget left over. Let's throw some diamonds in there. Why not? It'd be nice. Cool. Okay. Because JWST gets the gold, so Lucy gets the diamonds. I think that's fair. Yeah. And so Lucy is literally in the sky with diamonds. Nice.
Yep. And there's one last sort of twist to this.
Okay, so hang on. Just to sum up so far. Lucy is named after an ancient hominid creature who was discovered called Lucy, and it's a fossil, and that's related to the fact that we're looking at the fossils of the solar system. But Lucy, the fossil, was named after Lucy in the sky with diamonds, got something to do with that music being played in the camp and something like that. But Lucy is literally in the sky with diamonds now, and you're saying there's a fifth element. Go
There
on.
is, yeah. So on her way to the Trojan asteroids, Lucy will be flying through the asteroid belt and will be flying by a particular asteroid that is named Donald Johnson, the discoverer of Lucy the fossil.
No, really?
Absolutely.
They did that on purpose.
I suspect so.
They must have. Otherwise, can you imagine? It's like, wait, everyone, listen, look at this. We're just going straight past this. No, what are the odds? That's got to be a plant, right? That's very cool.
It's very, very funny, isn't it?
Wow, I love it. It's almost like they reverse engineered that one. We need a mission that's going to go past this particular asteroid called Lucy. What can we do with it? Well, there's the Trojan asteroids. We can send them out there. Okay, do it. That's great. Fantastic.
Well,
that's very cool.
I mean, I don't think it is coincidence. I mean, I'm not privy to all these kind of conversations that happen behind, I think, many closed doors. But the actual asteroid was discovered in 1981. Lucy the fossil was discovered in 1974.
Right.
But the asteroid was not named Daniel Johansen until 2015.
Right.
Which is suspiciously not long ago when Lucy, the telescope, the spacecraft mission, was in its kind of final stages of, we really want to do this.
So what you're saying is that it's conceivable that, as they said, we're going to be going through the asteroid belt quite close to this thing. It needs a proper name. What would be a really good name to give it? That's when we came up with.
Yeah. So I don't want to rain on people's parades too much here.
It's a really good story nonetheless. It makes a really nice narrative arc all the way out and all the way back. So that's cool. Nice.
And it's not just diamonds that Lucy's got on board.
Mm-hmm.
She's got a bit of gold.
Bit of gold. Well, that seems to be de rigueur at the moment. All the best spacecraft do.
Exactly. And Lucy's no different. She's got her own gold plaque, which has the date of her launch, as you might expect. Some pictures which show the position of all the planets when she was launched, and actually some pictures of the Earth which show where all the continents currently sit. Mm-hmm. I guess with the idea, the Earth evolves, the continents move.
Could be a really long time before anyone sees this plaque, is what you're saying?
Yeah, I mean, she's not designed to leave the solar system, so it's more like a time capsule for humanity, I think.
Right.
And there were 20, they call them messages from people. I sort of read some of these messages. Most of them are quotes from songs.
Well, I mean, that's what passes for wisdom in the modern age, I guess, isn't it?
Yeah, maybe.
What songs in particular?
Well, so there are quotes from each one of the Beatles, for example.
Well, I guess, going with the theme, yeah.
Brian May's got one on there.
Nice.
Carl Sagan, clearly, not from a song, but,
that's contractual, isn't it? I think Carl Sagan has to be.
Yep, Einstein, Martin Luther King.
Right. Any women involved?
There are not so many famous. Well, and it's not so much to me. I'm sure they are famous because
someone's heard of them. Yeah,
but there are some, and there's some in other languages as well, which I didn't read what they.
Well, that's nice. It's not just white Anglo men. Yeah.
No, but there is a slight dominance there. So, and there's just also a slight tendency towards kind of 70s, 80s rock music. I suspect, but
again, I can kind of see a theme here.
So going back to our sort of before we segued into Lucy and Sky and diamonds, etc. What are we actually going to learn from Lucy?
Yes,
about these fossils.
Yeah. There were 4 things. Yeah, there was composition, there was color, there was spin, and there was mass. Yeah,
and those things are going to tell us, hopefully, where these Trojans have come from. Where in the solar system's evolutionary history do they fit in that jigsaw puzzle? Because it's really not clear. I mean, trying to figure out the evolution of our solar system is hard enough.
It's complicated, right?
We're sitting here, 5 billion years into the evolution of the solar system, trying to figure out what happened, most of that history 4.5 billion years ago, when everything's just become a giant mess since then, right?
Yeah, because it's not like things just formed and then, that's the way they are forever and ever and ever. Like, things formed and then other things got in the way and things bashed in. Like, we've talked about this before, the early solar system was a real wild ride.
Absolutely.
Right? The big planets did some really nasty stuff to the smaller planets and all sorts of things along the way. And we're kind of left with this system that we have now, which kind of looks like everything's moving the way it's always moved, surely. But no, things have changed a lot.
Exactly. And what you mentioned there is one of the big theories that we'd like to understand about our solar system is migration, because planets didn't form in the places that they are now. Broadly speaking, like in terms of like the order, well, there's one exception about the order that I think we need to come back to.
Because there always is, yeah.
There's two planets that have probably switched places that I think we need to talk about in a later episode, because it's one of your newfound enigmas.
Oh, okay. Yep. Come back to that one.
Yep. But apart from that, broadly the planets formed in the kind of order that they are now, but they've moved over time. And modelling how they have moved over time is really quite tricky. Now, we think that the inner planets have undergone what we call type 1 migration, which kind of means not a lot of migration, but, you know, they don't have a lot of mass. The disk that was sort of the planets formed out of, this kind of circular disk of material, gas and dust, the leftover bits of the sun, didn't have a huge effect on them. They maybe migrated a little bit inwards. So Earth may have formed a little bit further out than it currently is and gone in a bit, but not, you know, too much to write home about.
Sure.
However, some very exciting stuff probably happened with the outer planets, so Jupiter onwards. So we have different models for migration, and probably Jupiter underwent what we call type 2 migration, which is that because it's so massive, it's actually cleared its own gap in the disk long before, you know, the sun started blowing the material out of the solar system. And that has a profound impact on its motion. It probably means it migrated inwards.
Okay. I mean, I would ask why, but I'm guessing that's complicated.
Yeah, I mean, if you just think about balance and gravity, when you start to upset that balance, then you start to upset the positions of planets.
Sure. Okay. I'll buy that.
So Jupiter probably moved inwards, and this is actually probably the same mechanism that we have for the hot Jupiters and exoplanets that we find today. So we find things that are the size of Jupiter and much, much bigger even, that are very, very close to their host star, and they can't possibly have formed there. Right. We know that they're way too big. They have to have formed beyond the snow line, beyond the point in space where water freezes. But so somehow they moved from beyond that point to being super close.
Really close. Yeah.
And so we think that this kind of type 2 migration is how they did it for the hot Jupiters.
And we know, this is a question, we know that Jupiter and maybe the others as well, the other big planets out beyond Jupiter, we know that they did this in the early
We've got some really good clues.
Yeah.
So there's a few different models out there, and you can pick your favorite one. Most of them have foundations in what we call the Nice model, which is an idea looking at you form the kind of the outer planets, and the outer planets kind of move inwards and then outwards as the broad kind of mechanism. And there's different subtleties. I mean, one of my favorites is that when we started off, Jupiter was kind of... So Jupiter sits at about just over 5 astronomical units from the sun now. But perhaps it formed at kind of 3.5, so quite a bit
That's a lot closer, yeah.
And then what happened was it started to undergo this type 2 migration. It started to move in. And what it did was start to disrupt the material that was at that time forming Mars and sort of kind of threw its weight around, shall we say.
And it's got a lot of weight to throw around.
In the inner solar system, yeah, just and maybe... So we know that Mars is smaller than we think it should be, possibly because Jupiter came and just kicked a lot of stuff that Mars should have had accreted onto it and kicked it away. And maybe there was a planet trying to form with the asteroid belt. Now it is.
Yeah, I was going to ask you about that.
And Jupiter kind of went, no,
you're not, no.
Not going to happen.
Not going to, sorry.
So you imagine Jupiter moving in and then what catches it? You know, what's going to stop it just going in and just colliding into the sun?
Beats me. It kind of feels like Jupiter can do what Jupiter likes.
Well, it turns out the second largest planet in the solar system has something to say about this. Saturn, yeah. So we think that then Jupiter hit a orbital resonance with Saturn. And that means that every time that Jupiter went round once in its orbit, Saturn went round twice.
Yeah,
other way round. Yeah, every time that Jupiter went round twice, Saturn went round once. So it's going slower.
Right. Yeah. It's easy to forget that there are other things, right? that Jupiter is this enormous influence, and yet, of course, you can't ignore this massive other planet out there. Yeah, long way away, but still has this big influence, and that has a tug on it every time it comes around. And that can do all sorts of crazy things.
Yeah, and that resonance ended up moving the planets backwards again.
Right.
Pulled Jupiter back to its 5 astronomical units, pulled Saturn back, did some horrible things to Neptune and Uranus as well. They should have been bigger than they are, but they got, collateral
Jupitered.
damage.
Yeah.
And probably threw in at some point we had this period where we knew that a lot of material was thrown onto the inner planets, what we call the late heavy bombardment. That's probably linked to that. But we also have this very mysterious puzzle where there shouldn't be any kind of water volatiles, these kind of chemical compounds that shouldn't exist in the inner solar system. They're not allowed.
Right.
The sun should have blasted them all away.
They clearly do, Emily.
Yeah.
Because that's us.
So the idea is that, yeah, exactly. We need the water and nitrogen, etc., for our atmosphere.
Don't take that away from us. We've got nothing left.
Well, we shouldn't have it. It really shouldn't be there. We should be much more like kind of Mars and just have kind of not much.
Yeah, okay.
But what we think happened was part of this kind of process of this migration was that the Kuiper belt was disrupted. Remember, that's the place just outside the planets where you got all those comets and icy stuff, lots of volatiles out there. Maybe a whole lot of that stuff was then thrown into the inner solar system and picked up by the planets later on.
So Jupiter and Saturn and the other big planets, they got a lot to answer for here. They got a lot that they are explaining.
Yeah, I mean,
themselves.
I think Mars is pretty peeved, but Earth should be kind of happy.
Mars did kind of miss out there. Not only is like, hey, I should have been bigger than this, right? You ripped me off there. But then where's the atmosphere? Come on, this is rubbish. Poor old Mars.
Yeah. But the bright side is we have lovely lakes and so on to
I mean, look,
enjoy on Earth.
It's a win for us. I just feel sorry for Mars. So, all right, there's a lot of questions there about how this thing that we call the solar system got to be the way it is now. And there's a lot of questions which we can point to Jupiter and go, you've got a lot of explaining to do, my friend. How does going and visiting these camps of Trojan asteroids help that?
Yeah, so these Trojans, we know they're old. We know they come from this very early point in the solar system.
So we know that already?
Yeah.
How do we know that
Well,
already?
like the asteroid belt, they're just leftover bits of the solar system.
Is it just simply that you couldn't have made something like that quickly? Like, we know it's not recent because, or can you actually look at it from this distance and go, that's an old rock?
Well, I think a bit of both. But
yeah.
So unlike Saturn's rings, which we think are quite new, that probably came from some moon or something like that, then the asteroid belt and the Trojan asteroids are very old. And we know we've visited some of the asteroid belt.
Right.
Okay. We know them very well. So the question is, are the Trojan asteroids related more to the kind of material that's found in the asteroid belt? Are they related more to the kind of material that was kind of in Jupiter's zone of influence? Is it kind of leftover bits of Jupiter? Or is it something more to do with these volatiles that were thrown into the early solar system? And do they contain any sign of these, like water ices and things like that?
Right. So you'd be able to tell the difference in a really quick flyby at 9 kilometers a second. You'd be able to see that kind of looks like asteroidy belty material, or that kind of looks like Jupiter-y material, or that kind of looks like Kuiper belt comety material. And those would all be a bit different.
Exactly.
Wow. That's cool. That's cool. So we will hopefully, if all goes well, like be able to figure that out. Figure out when and where these things came from.
And that's really helpful because I say we've got lots of models of how the solar system formed. And one I just explained is kind of a bit, it's called the Grand Tack sort of version of the Nice model. But there's loads of others. We've got something called a jumping Jupiter model where it jumps around.
I like that one.
Yeah.
My vote
That's a fun one.
goes to that one.
You know, we've got ones with more migration, ones with less migration, ones with extra planets that are no longer with us for various reasons. So there's a lot of question marks. We can build something that we think kind of basically happened, but the details, which are very important details, are very much unknown.
Yeah. I mean, look, I could build a model, but it doesn't mean that it's any more or less accurate. And what you need at some point is some data that's going to be able to actually fill in the small or enormous gaps in that model making. And this is one of those. This will kind of really help, I guess.
Absolutely. And what I love about it is this is kind of the last piece of, let's call it the accessible part of the solar system for us to visit. We've been to Mercury, we've been to Venus, we've been to Mars, we've been to the asteroid belt, been to Jupiter, blah, 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 whatever, beyond that.
All the other ones, yeah.
Haven't been to the Trojans. So I love that this is going to be, for us, a true voyage of discovery.
That's cool. I hadn't thought about that at the beginning of this conversation, that this is the last bit of the solar system, like as you say, the accessible solar system. There's a lot out there beyond the planets, which is a long way away, and it's really hard to get to and explore. But within the accessible bit, the bit that you could get to within, let's call it a decade, this is the last one?
It's the final easy to get to frontier.
Wow. Doesn't have the same ring to it, does it? You couldn't really make a science fiction series out of we're going to explore the easy to get to bits. That's not the point of Captain Kirk, is it? You'd never sell that to a network.
Maybe we should have gone with Yellow Submarine rather than Lucy in the Sky.
Well, that's 2 episodes in a row that we've gone out, at least in the vicinity of Jupiter. I think that's probably enough Jupiter for now. There's nothing against Jupiter. There's a lot going on Jupiter. We could spend the rest of Syzygy in and around Jupiter, but I think it's time to go and look at some other stuff next time. What do you reckon, Emily?
Yeah, well, we've got on the board now one of your new favourite Enigma planets.
Well, it's Neptune.
Yeah.
Kind of got to go and look at Neptune, don't we? I think there's a lot of questions to be answered there. Is Neptune the one that's turned on its side? Or is that Uranus?
Well, they're both off axis.
Look, save it. Let's not spoil that one. We will do that one, whether it's next or whether it's a couple down the track. We're going to do that one. Listen, Emily, if people wanted to get in touch with us and school us in how to pronounce all of these names of these Trojan asteroids, how could they get in touch?
So if you're very good at phonetic spelling in a condensed format, then you can try to tweet us.
That's right, because you've got just a very small number of characters in order to get your message across, yeah?
Yep, so you can get us at SyzygyPod. Now I can spell Syzygy, S-Y-Z-Y-G-Y.
You can spell it and you can pronounce it.
Yeah. Unlike most of the other names of these Trojans.
But if you can't pronounce your own podcast name, then what good are you? So SyzygyPod, at SyzygyPod for Twitter. Anywhere else?
Yeah, on Facebook.
Yeah?
Just shove it in that little search box. You'll find us, SyzygyPod.
Facebook, like all the others have this is where you can find us. And Facebook's just search for us. Just go and find it. You'll find us on there somewhere. Whatever Facebook calls itself next week when it changes its name. Instagram, we're on the Instagrams.
Yes, yeah. Some pretty pics going on there.
At SyzygyPod on Instagram.
Check out the launch picture that's coming up for this, Lucy. It's stunning.
Excellent. Looking forward to that. And, of course, you can just go to our website, syzygy.fm. All of our episodes are up on there with all of the info, all of the pictures, and there's a contact page where you can send us a hello, and there's a page where we thank all of our fabulous supporters, people who have donated actual cash to the show over the years every month to help us keep the electrons flowing through the website and to help us to do what we do when the world is opened back up after all of this stuff that's happening around the world. If you want to become one of those people that we have on our Great Wall of Thanks, you can go over to patreon.com/syzygypod and sign up to be a financial member of the show. And our thanks would be eternal. I think that would be awesome if you want to do that. The other way you can support the show is to tell everyone you know that there's this brilliant thing called Syzygy that you've been listening to, and they could do a hell of a lot worse than tune in to the next episode. So go and point them in the direction on their podcast player of choice. While they're there, they could give us a little review, give us a couple of stars, helps us to rise up through the noise. But there's enough of all of that. Emily, I'll catch you back here in a week or so.
Absolutely.
I'm really enjoying this regular recording thing again. I think we should keep this up.
Yeah, it's doing wonders for my sugar intake too.
Yes, indeed. Right, Emily, well, I'll see you in a week's time. See you later, everybody.
See you later.
Bye-bye.
I was going to study planetary science when I was a kid. I thought, I'm going to do planetary geology and I'm going to study rocks on the moon. That's literally what I told my parents.
Rocks on the moon.
I was a kid.
Yeah. What happened to that?
It turned out to do geology, you had to be quite fit to go climb mountains. And so I decided to stay home and look through telescopes instead.
But you're quite fit. You've walked across the country, for goodness sake.
Yeah, but I was a lazy teenager.
I love the idea of career choices being made around. Can I do it? Can I do it from the comfort of my couch? Is that possible? Yeah, easy.